So this is why I think maths gets hard. Okay, let's start out very simple. A function is essentially a relationship or expression involving one or more variables. I've created my function called function double. You give me a number from 1 to 10, I will give you double the output. Okay, you give me a 2, I'll give you a 4. You give me a 10, I give you a 20. Really simple stuff right now. Okay, I have a new function called triple. You give me a number between 1 and 100 and I give you triple that number. You give me 20, I give you 60. You give me 10, I give you 30. Still pretty easy right now. Let's do this one more time. I have a new function. I call it minus 10. You give me a number between 1 and 100 and I'll take away 10 from it. You give me 60, I give you 50. You give me 15, I give you 5. Okay, now let's try and put this all together. Let's say you have a function double, triple, minus 10, which are all part of one really big function. If you'll give me 1, I'll double it to 2, then triple it to 6, then I'll take away 10 and give you minus 4. If you give me the number 10, I will double it to 20, I will triple it to 60, and then I will take away 10 to give you 50. Okay, so later we're going to see some really complex functions that I'm just going to kind of gloss over. But I want you to imagine a really complex function is made up of lots of really small functions, and you keep going down lower and lower, and the functions are very simple. Add, subtract, minus, divide, but you need to do this a lot of times in a function, in a really big function, to make it work. So hopefully that kind of makes sense in a way. This is why maths is starting to get a lot harder. And as long as you remember loads of functions together, you'll see how the next few points relate. So this time I want you to work backwards. I am going to give you a function, question mark, question mark, question mark. We don't know its name, we don't know what it does, but I will give you a few clues. I will let you give me the number 1 to 9, and then I will give you an output, and I will only use plus, minus, divide, multiply. So, you give me a 1, I will now give you a 4. What function am I? How sure can you be? Okay, so you've given me a 1, I returned a 4 to you. Well, I think you can only be 2 options now. You could either be plus 3 or times 4. But there are only 2 options, so I think I'm going to guess 50-50. Either one could be correct. Okay, so you now give me a 2 and I return you an 8. What can I be? Well, you can only be a multiply by 4, and I am 100% certain that this function is multiply by 4. Look, I told you it was going to get harder. Right now we have a function called unknown. Unknown is 3 different functions. In each question mark you can put a number. In each box you may put an operation. What is the correct answer and how sure are you? Okay, so I think I worked it out that there are 46,656 different combinations, 80 of which are technically correct. You could have 6 times 4 times 1, you could have 9 times 8 divided by 3. I'm not going to list all of them, but you can see how difficult this actually is. So imagine now we come back to this as a complex question, and I say, listen, if you give me a number, let's say 1, I'll give you a number, let's say 1789.56. Do your best to work out what every single function is. Now that is almost impossible. Well, it's not impossible if you can improve each time. Like if you can sort of work out, hey, a green box has to be plus, a yellow box has to be minus. We can only use numbers 1 to 10. If you had these examples or these limitations, you might be able to make headway on this, but I hope you can understand how difficult it is to do this. And I want you to imagine all these functions are a physical problem in the world, and you're trying to figure it out. Okay, so let's say you're Galileo or Kepler and you want to look at how stars work for some reason. So this is what I'm thinking. Back then, they didn't have the luxury we had. They probably had some local charts in their local place, and their charts could be of orbits at random times. Imagine you get given, let's say, 20,000 different charts, which are fairly accurate, showing where the sun is, where the earth is, and what the date is. You need to somehow use this information to come up with some kind of formula or some kind of pattern to orbit. Honestly, it's not easy. It's not impossible, but it's not easy to do. And that's why maths gets hard. You've got to take a hard problem, use the tools you have, and work backwards rather than work forwards. So moving on from that, the next lesson is the universe, or the physical world we exist in, is not linear. So I picked about 4 examples of fluid mechanics, air pressure, radioactive decay, and chicken cell growth. So these are all real life examples or real life constraints you have to deal with, and you can see the maths for 2 or 3 of them. It's not easy, it's not linear, it's not nice, but it's the real world and you have to deal with it. So I am trying to go for more like a neuroscience AI PhD, and I'm reading some papers, and I don't 100% get this, but I do kind of understand what they're trying to do. You can see right now they have got to use very high level maths to model real situations, and that's why maths get harder after a while, because you're using your tools for harder and harder things. You need to put a lot of things together correctly. So 2 plus 2, pretty simple, 4. But when you go to the question about circles and lines, you have to use trigonometry, addition, subtraction, at an angle, you need to know the perpendicular. So you need to understand all these things and put them together in the correct way. Okay, so I was trying to solve this example to show you about it, but it took me 15 minutes and I had to look back at what I was missing. So let me try and walk through. You need to understand circle theorem, you need to understand Pythagoras, you need to understand how to manipulate these things, you need to understand how to find the angles adjacent, so the angles opposite each other. So line 1 has its equation, and a line which is opposite to it directly will have the same equation -1. The slope, when both slopes multiply by each other, they should equal -1. So I know m should equal 7. Again, poor example of me explaining it, but I just want to show you, to get the question correct, I had to put loads of things together. The next thing is that your hand stops getting held as you get older. So, another reason why maths get hard is essentially as you move up the level of difficulty by age, your hand gets held less and less. And nobody tells you, hey, we're going to stop holding your hand now, you've got to figure it out for yourself. And what I mean by that is essentially up to GCSE, which is 16-year-old and even 18-year-old, so much of the maths you do is your hand is held, but you don't realize it. Since I'm applying for a PhD now, and I'm looking back at my A-level doing it just for the video as well, I've noticed, oh my god, I struggled with this so much in the beginning, but there are kind of a few hints and tricks that the book has given you. So what do I mean by this? So this is a very, very, very hard circle question. However, if you have read everything before this and understood it, we have given you enough tools to build this. And when I'm just stuck and I need to intuit an answer, and I'm like, I don't know how to do this, I realize, no, I know for A-level, and even for university, because I'm much older now, that they have given you every tool you need to solve this problem. Like, it's a clear, easy problem to solve. It's not a real world hard problem. You should be able to figure it out. When you get to the very top now, because I am looking at PhDs at this level, I'm going to show you two different things now. You have a network, a action potential of a nerve cell, okay? But this nerve cell is like 1 millisecond. And we want to take a snapshot of loads of pictures, so millisecond 1, millisecond 2, millisecond 3, and put them all together to draw conclusions. Now, this is a lot harder to do because what we need to do is look at all the work out there and do something completely new that is slightly different. But that's kind of contradictory, but when it comes to PhD level, there are no easy answers because a lot of these questions here, up A level here, you'll be surprised. They'll give you something like, let's just say, x squared plus 20x plus, I don't know, 80, for example. And whenever you solve it, you have very nice numbers. Sometimes I'll get like 100, I'll get 200, I'll get 60. I'm going to get nice whole numbers. And when I've got a nice whole number, I know for a fact that this is most likely correct. But in the real world, when you're applying real maths, you're going to get horrible numbers. You might get, let's just say, a 65.9437821, and there's no way to know if this is correct at a glance. But in my exams, I'm like, hey, this answer feels correct, this answer looks correct, it's probably correct. And that's something you kind of lose as you go older and older. So the next thing I want to talk about is representations and having to jump from one to the other properly. I talked about this in the maths lesson I've learnt before, but as I've gotten older, I've realised the higher up you go, the more you realise maths is not about numbers, maths is about abstractions and relationships to each other. What do I mean by this? Okay, this is a phone, this is a pen, this is a set of glasses, but there is nothing that is the number 2. The number 2 is just a concept or abstraction we understand. And it makes sense for humans to use the exact same abstractions because once upon a time there was a rocket, which was a joint project between, I think, America and the UK. One person used milliliters, the other person used centiliters, I think, or the other thing. They used the wrong amount of fuel and bang, rocket exploded. So that is why it makes sense for everyone to use the same abstractions. But how you choose to represent something is important. Each of these representations has its own unique characteristics and patterns behind them. And as you move further and further up the ladder, you start to realize, for example, this circle problem, I had to turn this into a quadratic problem. So I went in a way from this shape to maybe let's just say a quadratic function, you know? I turned one into the other. Or in fact, I broke this down into many small parts, and one of the parts was a quadratic, but at the same time, I knew how to bring this piece back up together. So you can maybe think about it like, I broke apart something really complex into other things. Maybe you have a massive Lego set, and you break the Lego into all its small pieces, and you build something different. You need to be able to build the thing you had originally and do that across the way. That's the best way to explain it, and let me give you a more concrete example. When it comes to brains and neural signals, let's assume we have a perfect device that can measure signals. So right now, I have this messed up data, very messy, very unclean. I somehow need to translate that into a nice thing for a human to use. And that's not easy to do. As you get to a higher level, I feel like you have to translate one abstraction to another abstraction and understand what you're doing. So I want to turn all these messy signals into nice numbers. I want to turn this into, let's say, a matrix of 4 by 4 at second 1, 4 by 4 at second 2. And let's just say 1, 2, 3, 4. Now, this data is in a form I can maybe use and understand neater. Or I can maybe write a program to analyze this kind of data. But at the same time, any changes I make to this, I need to understand how it will affect that. And that is, I think, another thing I struggled to learn in the beginning, but now I'm seeing when you're at PhD level, you have to move between one model to the other level. So one thing that inspired this video was recently I was doing some matrix multiplication learning, and then I remember, hey, I saw an academic paper use the exact same thing. So I looked up the paper and I sat down and I didn't understand it, but then I spent a couple of hours on it and I'm like, okay, I sort of kind of get what they're doing. So essentially they're just looking at the flow of I think blood or something through the brain, or they're looking at how matter forms in a certain area, and they're using vector fields to do this. So you can just take a look at this now and you say, hey, this isn't too complex, like I actually can do this easily, you know. Yes, and then you can see different parts here. This is getting a little bit harder, but I'm still within the striking range, and I realized I'm just sitting here, and when you want to do hard problems, you kind of have to use the maths. And the further up you go, the better your understanding of abstractions have to be. And another great example of this was when I was in an interview for AMD, which I didn't get because fair enough. I was speaking to the person and I said, I think it does this. But every time I said, I think it does this, he stopped me and says, what do you mean? You think it does this? Are you sure? And I was like, well, maybe. Every time I said, I think, he stopped me and said, no, no, no. Tell me you are sure, or tell me you are not sure. And that's what I've noticed when you go higher up. You have less room for mistakes, as in there's less hand holding, but you need to be more sure than ever before. So this problem here, the modeling white matter, I don't think there's ever going to be a set of numbers where it's like, oh, this graph equals 100, 200, 300. It's going to be a messy, messy thing. And you need to understand how this messy, messy thing works. So I would love to end this on some hints or tricks or tips of how to do maths better, but I don't think I can. The only thing I think I can say is the more you understand how hard maths is, I think the further up you've come. And there is no way to sugarcoat this. The universe is a cold, indifferent place in this moving towards a state of entropy. Physics doesn't behave for you. Electricity doesn't behave for you. You can sit, cry, moan as much as you want to, but the electrons in atoms are never going to move linearly. And once you want to understand how to use maths, and once you're forced to use it, like for example, you can just get by life using mental maths perfectly fine. But if you go into a role that needs maths, I found when you need maths, you need maths. Like when you need to use calculus, you need to use calculus. And when you need to use it, it's not something you can just learn in a couple of hours. You need to put so many foundations in to effectively use it. And that's going to be a hard difference to understand. Like most people, even most people watching this video, probably won't ever need to use maths like the way I'll need to. You want to play around with some AI tools to generate images. You can just take the tool, add in a few settings, like try to put pictures in Picasso, try to put pictures in the style of minimalism, which is very simple to do. But what I'll need to do, for example, is I'll need to go and understand the underlying maths behind this. And you have to put so many correct pieces together, understand so many things about how this works. For example, right now my university course now, I've got my project which is worth 60%. I have to essentially run a few neural nets and models. And essentially I can go on Google and say, okay, give me some examples. And they might give me examples with a certain confidence level, a certain batch size, a certain amount of a certain set of preset values for the X predict, X train. let's just say it's 0.7. One question I was asked in my data science unit was, why did you pick the number 0.7? And Google's paper says for data sinks, we use the number 0.8 as a dampening factor. What does that mean? Why use 0.8? Why not use 0.7? And honestly, I did not know then. I kind of know a little bit now, but not well enough to explain. And yeah, that is kind of where I am with maths now. Hopefully you got something from this video.